G'day chemistry students. In this video, we're covering dot point 6.1.5. In particular, we're looking at the enthalpy of neutralization and how to measure it. Let's get into it. So already we've done experiments involving calorimetry. A lot of the experiments that we did looked like one of these guys. It's the one on the left in particular, when we were burning alcohols and finding the enthalpy of combustion. So this setup is one way that you can measure energy changes in a reaction. Here we released energy from the spirit burner and measured how much energy was being absorbed by the water. What we found was, though, that our results weren't matching the literature data that we were able to find for the enthalpy of combustion for all the alcohols that we used. What we determined was that energy was being lost to the surroundings, being lost to the beaker, and I think that we were using a tripod and a gauze mat as well. So the energy was being lost to the metals that were there as well, meaning that not all the energy that was being released from the spirit burner was going into the water, which meant that we weren't able to measure it. And when we were doing our calculations, converting the energy absorbed by the water to a molar enthalpy of combustion, we weren't able to account for all the energy that was being released. We talked about then that a better way of going about doing an experiment like that was using a bomb calorimeter, where the reaction would happen inside a vessel triggered by some sort of electrical current. The energy would all be released in this container and all of it would transfer to the water, none of it escaping because of the heavy insulation around the outside. Therefore, all energy that was coming from the reaction would be able to be measured by the thermometer, leading to a much more accurate result. Now, when we're doing enthalpy of neutralization, these methods don't make as much sense. We're probably going to be using a calorimeter, which looks a lot more like this. So we've already tried to do some calorimetry using a setup like this one, when we were dissolving different kinds of substances and measuring the enthalpy changes that were there. Very similarly, we're going to be putting all of our chemicals together in the one container and measuring the energy changes in the water. When we were dissolving, we were doing energy changes in a solution. Same thing here when we're doing our neutralization reactions. Everything's going to be in the same solution, so we can use a much simpler setup like this one. When we're doing our calculations, the one thing that's in your data sheet is that Q is equal to MC delta T, where Q in particular is the energy change that's in the absorbing material, which in most cases is water, the thing that's actually taking in the energy or giving the energy to the system so that the reaction can proceed. In particular, we need to be looking at C here, the specific heat capacity of water, which is given to us in our data sheet. If we're using a different substance other than water to absorb energy, if we're doing a problem in exam conditions, that data needs to be given to you. So just like we did in module 4, we can calculate energy changes in a substance using Q, M, C, and delta T, measuring all of the changes that happen to that substance that's either absorbing or releasing energy, and using that Q value to calculate enthalpy, where delta H of the reaction is equal to negative Q divided by N, the number of moles of whatever's happening in the reaction. I'll come back to N in a minute. This formula here is not a part of your data sheet. It is something that needs to be remembered. That when we're looking at, say, the energy being released or absorbed by the reaction, that the absorbing or giving substance is going to experience the opposite energy change. So for example, if delta H here is negative, that the reaction is releasing energy, that we're going to expect Q to be positive because the substance is going to absorb that energy released. On the flip side, if we have delta H and delta H is positive because the reaction is gaining energy to proceed forwards, that's going to mean that the surroundings are going to give away energy to it, meaning that Q of the surroundings is going to be negative. So I'm not going to do a calculation in this video in particular, but if you need some practice, maybe using these equations, or need a bit of a refresher, maybe go back to the module 4 videos and have a quick refresher there, maybe do a couple of practice questions. What I want to talk about finally here is the idea that enthalpy of neutralization and enthalpy of combustion are two different things. That when we're looking at enthalpy of combustion, what we're looking at is measuring the energy change per mole of fuel that's being consumed. So if I've burnt a mole of ethanol, how much energy has been released. So we find out how much energy has been taken up by the water, make that negative because we're looking at the energy being released, and dividing that by the amount of fuel that was actually burnt in the reaction. What that means is for delta H of combustion is that regardless of what substance we're burning, we have a clear comparison between each substance. So if I have the delta H of one substance being 100 and the delta H of another substance being 200, we know that the second fuel releases twice as much energy per mole consumed. On the flip side, when we're looking at neutralization, we're measuring the energy change per mole of water produced. The thing that's common in every neutralization reaction based on our general equation, at least when we're looking at aqueous neutralization anyway, is that we are producing water. That is the common factor between all of those substances. So it makes sense then to be calculating the enthalpy of neutralization based on how much water would be produced. So to do a calculation like that, you would need to figure out theoretically, based on the amount of acid and base that you've got, how much water would be produced in that context, and then apply that to the delta H calculation. There's a quick comparison. Enthalpy of combustion is determined by the amount of fuel consumed. Enthalpy of neutralization is determined by the amount of water produced. This is what we're going to be focusing on for Module 6. This is what we'll come back to in Module 7 when we look at the enthalpy of combustion of alcohols again. So when you're doing a calculation, the stoichiometry of the water is really, really, really important. So here we can see that the heat of neutralization is going to be based on the fact that 2 moles of water are being produced for every 2 moles of hydrochloric acid and for every 1 mole of magnesium hydroxide. Keep in mind as well that when we're doing enthalpy of neutralization, we are assuming that we are working in aqueous conditions where there is water being produced. Obviously, if there are acid-base reactions, neutralization reactions where that's not occurring, we don't see water produced. Those will be measured in a different way, but that's not really within the scope of the course. Thank you very much, everyone. In the next video, we're going to be focusing on dissociation of acids and bases, how they form ions, and what that means for the strength of bases. We are going to be throwing around terms like strong acid, strong base, weak base. And it's something that, while it may seem intuitive, is not a concept that we have covered in any kind of science before. So until then, have a good one.